So we're doing vector and parametric equations of a plane. Now remember, a plane is a two-dimensional space in three-dimensional worlds. Okay, and we'll try to draw a picture of it to try to make sense of it. Let's talk about these rules and then we'll get into it. In 3 space, the vector r naught, if it's defined as x naught, y naught, z naught, is determined by a point on a plane, and vector A and vector B are directional vectors. Okay, so very similar to our vector equation of just a vector itself, not a plane. We start with our r naught, and then we have a directional vector. But there's actually 2 directional vectors here. And we're going to talk about why you need 2 directional vectors for a plane in a minute, where normally with just a vector itself or a line, we only need 1 directional vector. For a plane, we have to have a second one involved. Okay? And the parametric form of this is very similar again. Before it was some point and a scalar of the directional vector. Well, this time it's a some point and a scalar of the first directional vector and a scalar of the second directional vector. Putting it together the exact same way we would have before, and there are no symmetric equations of a plane. Okay, so let's talk about a plane. And oh, I wonder if I have shapes that'll help with this. Yes. Okay, let's think of a plane. Oh yeah, that's great. There we go. So we got a plane. Now, when we talk about a plane, again, like I said, we're talking about a 2-dimensional surface. So, let's say we are in 3 space here. Something like this. Okay. And this is our x, z, and y axis. So we're in 3 space, and this parallelogram represents a plane. Let's say that this plane, remember we talked about proving that 2 vectors can represent any vector in 2 space. Okay? And that idea comes into play here, where let's say that our first line here is technically a vector, and our second line is technically a vector. We'll call them vectors m and n. Okay? Vector m, vector n. These 2 vectors, any scalar of them can represent any vector or line in this space. Okay? And that's when we were talking about how 2 vectors can represent anything in 2 space. Okay? We can make any scalar of it. We can shrink these. So for instance, we'll get an example of that. Say I were to have shrunk vector m. Okay? I have some scalar of it. We'll call it s actually. Some scalar s of vector m. And again, some scalar t of vector n becomes this resultant vector, which we'll call vector r. Okay. So these 2 vectors can represent anything in this space, which means that these 2 vectors can represent the entire plane, or the entire 2-dimensional plane in 3 space. Okay. So what we do from there is these 2 vectors, in order to represent the plane, we set them up as directional vectors. Okay. So our direction vectors here, I'm going to call vector m. We're going to say it's a little over the horizon, just to help us out. Sorry. And direction vector n. Okay? We're going to change the names of them to relate to our equation. This will be directional vector A and directional vector B. So these direction vectors represent this plane. Okay? And they help us represent them by the directional vectors coming from the origin, right? This is kind of like our OA point and our OB point. That gives us vector A and B. Those 2 directional vectors represent that plane. The only difference is they start at the origin. Because they start at the origin, it will help us with a lot of our calculations. Okay? Instead of having to find points in 3 space, we can always just assume it's starting at the origin and do our calculations from there. That's why they've set the formula up this way. And it's the same idea we did with a directional vector of just a line. It always goes from the origin so that we can calculate things a little easier. Okay? Now, in order to calculate a plane, they've given us 4 things that we need. So the first thing we're going to need is a line and a point not on that line, but on the same plane. So let's use this plane again. So I have this plane again. First thing we need, A, is a line. So we have our line. And we need some point on that line. Or sorry, on that plane that's not on the line to calculate this plane. And they use the plane, they use the symbol pi here to represent the plane. Okay? So pi represents this whole plane. We can determine any plane with at least these 2 points. If we have a line and a point, we can also determine a plane. Should have made this a little smaller. Okay, we're just going to move those around. Sorry about this. Here's our line. The plane is called pi. And some point on that plane. There we go. This way I have more room. Copy. Alright. The next thing we need, or the next thing we can use to determine, are 3 separate points all on the plane. If we have 3 separate points, we can also determine our plane. So we'll call them point A, B, and C. If we have 3 points on the same plane, we can determine a plane. That's our second requirement. Our third requirement for a plane is 2 intersecting lines on the same plane. Okay. So if we have 2 intersecting lines here, we'll just call them line 1 and line 2. L1, L2. We can determine a plane. And finally, the fourth thing we can use are 2 parallel lines on a plane. All of these things need to clearly be on the same plane, and, well, technically if we have just 2 lines, we will be on the same plane when referring them to each other. Okay. So as long as they're parallel, we can determine our plane. So these are the requirements for doing it. We're going to jump into a question and try to solve using some linear combinations. We're going to try to solve some of the equations of the plane, whether in vector form or parametric form.